Welcome to the presentation of our paper on a deep learning approach for lane detection. This is the outline of the presentation. First, I will briefly talk about lane detection, its challenge and existing methods. Then I will cover details of our proposed lane detection method and the results we achieved. Finally, I will finish the presentation with the concluding remarks. When we manually drive our vehicles, we need to be in the lane almost all the time for our own safety, as well as for smooth traffic flow. Similarly, we expect autonomous vehicles to do the same. To achieve that, autonomous vehicles need to detect lanes. This suggests that lane detection is one of the key components of autonomous vehicle or advanced driver assistant technology. So in ADAS system, lane detection is a part of lane keep assist or lane departure warning features. Whereas in autonomous vehicles, lane detection could be used as part of the lateral and longitudinal control system module or the localization module. So in general, lane detection is simply identifying the region, usually delimited by white and yellow paintings on the road. Therefore, the main features needed to detect lanes is the paintings on the road, which we call them lane markings. So in some cases, curbs and guardrails can also be considered as visual cues or features to determine lane boundaries. So the main challenges with lane detection is that lane features or markings are not always easy to detect or extract for the following reasons. One, we may have lighting change or like glares as shown in this picture, and we may have shadows from trees, bridges, or other vehicles on the road, interference from other road signs, especially in urban roads, road texture variations, and edged or faint lane markings can make the feature extraction really hard. Now let's look at the lane detection methods. Based on how the way image data is processed to determine the lane boundaries, we can group lane detectors into two main categories. One is a conventional image processing method, and the other one is deep learning method or data-driven approach. So lane detectors based on conventional image processing methods use various parameters and thresholds to extract the lane markings, which are all determined or tuned manually. As a consequence, the detector may fail to adapt well to various environmental challenges. The learning-based method, which are mostly semantic or instance segmentation or end-to-end deep learning methods to estimate lanes. In general, the performance of this group of methods is better than the conventional method under various challenging conditions, as long as the models are trained very well. However, the drawback of deep learning method is slow inference speed due to many convolutional layers in the model architecture, which is the main motivation of this paper. So if the state-of-the-art lane detectors are in general slow to produce lane information, they may not be really applicable for autonomous vehicles that require real-time operations. So this paper aims to develop a lightweight deep learning-based detector that can fulfill the real-time needs of self-driving cars without requiring GPU acceleration. So the general idea of our approach is that instead of considering each pixel in the image to extract lane features, like semantic or instance segmentation, we consider a small image patch at a time and determine if it contains layer marking or not. Then we collect each image patch containing lane markings and further process to find out the lane boundaries. So here is the block diagram representation of our proposed method. So the convolutional neural network model is used as a feature extractor, and the output features are further processed, like clustered and curve fitted to find the lane lines or boundaries. Here is the feature extraction. It's performed by first defining region of interest, as shown by the red line. Then the image patches are taken from the region of interest, and each patch passes through the CNN model or the convolutional neural network model. So the output of the model prediction is placed in a matrix form, as shown here, where each matrix element contains patch position and prediction values, like alpha M, alpha B, where alpha M is the confidence level for lane marking and alpha B is for background. So the next step is to filter the relevant image patches containing only lane markings. And the average intensity location is calculated as shown in this figure, where the red color indicates the average location of the lane markings in the patch. And this filtered matrix is stored in a new two-dimensional vector represented by P perspective. So then we transform the view from perspective to a top view or bird's eye view by simply multiplying each element of this P perspective 2D vector by a 3x3 transformation matrix H, which is kind of standard procedure of homography. The next procedure in the post-processing is clustering. Here we used a custom-made clustering algorithm that uses distance and angle as a criteria, where D is a distance between feature points in different rows, and angle alpha is the angle between the line segment formed by the feature points under consideration and a vertical line. So using these parameters as a criteria, our clustering algorithm results in several clusters that potentially represent separate lane boundaries as shown in this image. So this is the clustering algorithm pseudocode. And this figure simply shows the sample result of the clustering method, which are indicated by these cyan color arrows. So once we got several clusters, our next step is sorting the clusters based on the number of feature points. So the cluster with higher number of points is selected for curve fitting with second order polynomial, and it's used as reference curve to search the remaining lane boundaries. We know that most lanes have fixed widths and lane boundaries are usually parallel. So using this assumption, we simply shift the reference curve, which is shown in green here, by an average lane width LW and search feature points around that region, as shown by these orange dotted lines. If a significant number of feature points are obtained around this region, then another curve fitting is applied to the points collected in that region. And this way, the lane boundaries can be found, which is as shown in these orange colored curves. So at this stage, we have all the lane boundaries modeled by a second order polynomial as shown here. So the experimental results. So to train our model, we collected about 40,000 image patches of each size 16 by 64 pixels from various sources. So 50% of this data contains lane markings, and the remaining 50% of data contains just background, no lane markings, as shown in this image. To evaluate the performance of our method, we considered two public datasets, the Caltech and the KITTI dataset. So for the Caltech dataset, we manually labeled more than 580 images as a ground truth, which is shown by these green sample discrete dots. As a performance measure, we used error or the offset between the ground truth and the prediction, as shown by this last figure. It's just comparison between the ground truth and the estimated or the predicted lane boundaries. So we consider the prediction correct if the error or the offset for at least 70% of the discrete points is less than 15 pixels. Otherwise, prediction is considered wrong or false negative. So this table shows the detection accuracy of our method, which is more than 92%. And this is, I believe, reasonable performance. So these image frames also show how robust our detector is against strong shadow and some interference by another road sign. So similarly, we also tested on the KITTI dataset, and the KITTI dataset has got already labeled ground truth data and evaluation script, and it uses precision, recall, false positive, and false negative rates as performance measures. So here we got very low false positive and false negative rates and very high recall value, and of course reasonable average precision and max F. So this is in general a competitive performance obtained from our proposed method, especially considering considering that many of the images in this dataset do not contain one of the Egolian boundaries. So this is actually a very good performance given that reason. So we have a demonstration video on this YouTube link. And the other performance measure is runtime efficiency. And we tested our method on 3 computer platforms targeting only CPUs. On average, our method runs at 28 frames per second, which is enough for real-time operations of self-driving vehicles. So our main computer, which is the Crystal Rugged server, which contains Intel Xeon Scalable CPUs, has got 88 cores. But out of this, we used only 8 cores for the lane detection part. So to conclude, I talked about lane detection challenge and the common techniques, including the issues related to each detection approach. So we proposed a simple deep convolutional neural network that can detect lanes at a comparable accuracy with respect to these state-of-the-art solutions. And our detector can run at 28 frames per second on CPU platforms with up to 8 cores, which is enough for real-time needs of autonomous vehicles. So in fact, our detector is tested on our test vehicle, which is a Chevy Bolt electric vehicle provided by GM. It's integrated with other software modules, and it proved that it actually works in real time. Thank you.